Hello and welcome to Technically Speaking, where scientists and engineers come together to chat about a common interest, share knowledge and satisfy some curiosity. I'm Antonia and I'm joined by Laura to talk about a new process being developed to dissolve common plastics found in clothing. So Laura, why does this excite you?
We talked about, essentially we were talking about glass recycling in an episode a little while ago, and how glass isn't necessarily going to be included in a deposit return scheme in the UK. And we looked at how recycling glass compares to recycling plastic. And I was astounded that they only use mechanical methods for recycling plastic and not chemical ones. This is a chemical method that's being developed, and the difference between this and other methods is that it seems to be able to separate out lots of different fibres, so you don't need to pre-sort your plastic. You can just shove your clothing fibres in there and it goes to work, in theory. I mean, this is lab scale at the minute. But chemical methods are like the holy grail of plastic recycling, so it just sounds like a really promising way to go.
Yeah, separating does seem to be one of the challenges with recycling in general. That might even include colour.
Yeah, exactly. We've mentioned in episodes previously that plastics come in a variety of types and they have lots of different additives added to them. Can't say that word. Things. And this sounds like a process that could get around a lot of that.
And not to mention just contaminants, because people don't exactly keep their waste in a nice shelter. It might not have been clean to start with. So, yeah, if we can dissolve the plastic, maybe we can actually recover and recycle more of it. So, should we look into this published research then?
Yeah, so it came out, I think it was summer last year, and they essentially use a zinc oxide catalyst and ethylene glycol to turn polyethylene tetraphthalate, or PET, polyester, in clothing, into another tetraphthalate, the monomer form of the polymer, and they use some microwaves and some heat to make the reaction happen really efficiently. They put clothing fibres in there, mixed fibres, and the cotton and nylon weren't really affected by this process. Well, the nylon did degrade a little bit, but they could still separate all these different components out.
I mean, this sounds good to me, because the first thing when you said zinc oxide, I thought, oh, that's a fairly easy catalyst and fairly cheap compared to some other processes which are catalyzed with, say, platinum. Not as cheap. And
this is why people like stealing catalytic converters from cars, isn't it? Because of platinum.
Yes, I have been a victim. Story for another time.
Yes.
And ethylene glycol, I think, is antifreeze.
Okay, so quite common as well.
Yeah, and a microwave. So what I'm learning here is, could I do this at home?
It's worth giving it a go, isn't it? Yeah, in the research article, they use an off-the-shelf microwave reactor. So these are things that you would find in a lab. So you use the microwaves to help you synthesize chemicals, usually, or break them down, it would turn out. It did have quite a tiny capacity, and I don't know how much control you'd need over the, I don't know, how you're applying the microwaves or how fine control over the heat you'd need.
You said it's a special reactor, not just a microwave. And the tiny amount, how small amounts can I put in it?
When I, being a massive geek, looked at the technical specs for the microwave reactor they were using.
Of course.
Yeah, why not?
Gotta look up spec sheets.
20 milliliter vials. So they were using just 0.5 gram of textile material in 5 ml of ethylene glycol and 5 milligrams of the catalyst. So really tiny amounts they were working with. No reason why you couldn't stick that in your microwave at home, I suppose.
Yeah, maybe I'll be able to afford like 5 milligrams of very, very good quality zinc oxide, not just stuff that was in my sunscreen.
I was going to say, zinc oxide's in quite a lot of cosmetic products, isn't it? So could you just like stick some moisturiser in there with your antifreeze in your clothing? I suspect there would be some safety implications of that. I don't know what sort of fumes you'd be getting given off then.
And there are like too many other components then, aren't there? If I just microwave moisturiser plus metal plus plus some fabric, I think that might start a fire.
Or maybe. I mean, you need to get it at a temperature. I think they used 210 degrees Celsius for 15 minutes in their optimal reaction scheme. So you also need to get your components up to that temperature as well.
I don't know what temperature a microwave normally gets to, because I suppose it's not really a controlled temperature thing. It's just trying to vibrate water molecules, and so however hot that gets.
Yeah, so you should want to boil water, I guess, 100 degrees. So probably not hot enough. I don't know. I mean, we should do some experiments. I mean, we are using tiny amounts here, half a gram of material.
Maybe I'll leave it to someone with better resources, better fume cupboards and things like that.
Makes sense.
Never mind the home experiment. Let's go back to the actual research.
I think that would be quite a good idea. All right, then. When most research looks at just breaking down pure PET, they did that, but they also looked at what happens when you take some just clothing they got from a charity shop or Goodwill and put that in their microwave reactor with these other chemicals. And they looked at like the dyes that came off and whether different coatings on the fabric affected the efficiency of the reaction. So they found that ones that were UV resistant or fire retardant didn't dissolve quite so well. Which kind of makes sense because they're putting this at 210 degrees C, so the fire retardant would retard any reaction.
Is that how fire retardants work? I've never actually thought about it.
Yeah, I covered this with Roeda when we were talking about things to do with fire ages ago. And the chemicals that you use to treat fabrics, they basically just kind of melt over the surface of the fabric, preventing things from getting to it. So if you've got a fire and you've got oxygen in the room feeding the fire, the oxygen can't get to your flammable materials.
So yeah, if you wanted to do any sort of reaction, not just combustion, the fire retardant coating would be in the way.
Yeah, so they did say there may have to be some pre-treatment when they eventually get onto doing this industrial scale. So it may be that you don't just stick whatever your fabrics are in your process and out pops some monomers of your PET and some cotton fibres and some nylon and some elastane monomers. You'd have to do a little bit of pre-treatment, which is a little bit disappointing because the aim is that you can just stick whatever you want in there. But it's a step beyond what people have done so far, so it's a step forward.
Yeah, and I was surprised because the difference was still a 95% yield if it was completely just undyed material, and dyed made it 80, at most 70%, which is good. But yeah, the fire retardant material down to 10% definitely needs some work.
Yeah, and they did say that the dyes tended to end up in the ethylene glycol, which you could then separate them back out, so you could potentially reuse them as well. I think slightly disappointing is that you may not be able to use the cotton fibres to make new clothing afterwards. Unsurprisingly, the synthetics can all be broken down into their monomers and then put back into a process again. But the natural fibres, they're degrading anyway as people use them in their clothing. Every time you wash your clothes, the fibres get a little bit more fluffy and fragile, don't they? So you would normally throw cotton containing clothing out once it's completely worn out. Well, I do. Some people don't. At which point the cotton fibres probably ain't in great shape anyway. So when they go into this process and they're cut up and they're heated again, they get slightly more degraded. And I think they said in the research article in their discussion that there are other things they could be used for. But I don't think they said they could just be used for fertilizer for cotton fields, which to me seems really obvious. So it would still be circular in that respect.
I suppose if it's all degraded, it's come out of this recycling process. It's not just going to be cotton. It's going to be slightly ethylene glycol-y with a bit of dye. At that point, is that something we want to throw on a cotton field to try and grow more cotton?
Well, I think they said that the cotton could be washed to remove the reaction product, so you would get just cotton back.
Oh, okay, well... Or maybe just where the recycling plant is just isn't where the cotton is growing.
Maybe not. They did say there are lots of uses for it, and maybe that's why they didn't suggest using it as fertilizer for cotton fields, because there's no guarantee it would make sense.
But the idea definitely is promising, isn't it? You know, your waste material becomes your feedstock.
Exactly. Yeah, working towards an actual circular economy where the thing you recycle actually gets recycled back into the same thing.
So we stick in whatever fabrics, and then we get the monomers of the PET, and then it could just be anything. It could be a plastic bottle, not just clothing.
Potentially, yeah. So you would use it for, I guess, whatever was needed most. I mean, you would think if you're being circular, you turn it back into clothing, but I guess there's no reason that you have to. If people suddenly start buying fewer items of clothing, whereas for some strange reason, the use of single-use plastic suddenly keeps increasing when we're meant to be decreasing it.
I wonder, would it make synthetic fabrics more popular if you know it can be recycled, or natural fibres because they're almost more one use because they're less high quality at that point?
Yeah, I've had this same thought as well, because I've been trying to minimize buying synthetic fibres and going for like just a cotton t-shirt rather than a cotton t-shirt with spandex in it, because I can cut it up and put it on my compost heap potentially if it's been dyed using water-based dyes, or I can send it back to the company it's come from because they're like, yeah, send it back, it's organic cotton, we want to keep using it.
That's a cool initiative.
Yeah, but you're right, if synthetics become more circular and more reusable, maybe I would switch to that. My only question then is, well, what about microplastics? So every time you wash your synthetics, little fibres break off and end up in the water supply.
Well,
and this is a big area of research, isn't it? It's not a lot known about what it does in biological systems.
yeah, I suppose if it was a wastewater, could we put the wastewater through the chemical recycling process? Otherwise, I've heard of research where enzymes had actually developed in bacteria that could break down plastic. So chuck in some bacteria.
Yeah, I've heard a few things about this as well, and I imagine if it's in a wastewater stream, there's not a really high concentration of microplastics, so I don't know how effective the enzymes would be, or if you'd want to concentrate the microplastics somehow first to make the reaction more efficient.
I suppose if you just wanted to break it down, or did you want to actually try and recover, then yeah, you would want to concentrate it. Just simply get a filter to capture whatever was there. And then you're still going to have a lot of different things in your wastewater.
I think that's the challenge from what another episode from a long time ago from our water engineer Gali was saying, that it's difficult to get them out because there are so many other things in there.
I'd come across this as a attachment to washing machines, so you can get it sort of at the source. It's a filter that you attach onto the drain of your washing machine, and when the filter comes blocked, it puts it into bypass mode, so instead of going through the filter, it will go out into the waste stream, but then it'll flash up to tell you to change filter. And this company that's developed it wants it to be an entirely circular process. You send them the filter and they will recover the fibres off it and try and turn it into something new.
Ah, very nice. I do wonder how many people just wouldn't bother doing that. Like the waste pipe from our washing machine is really difficult to get to. I'm not pulling the washing machine out every single time I want to change the filter.
Yeah, I was thinking this, if I got it for myself, where would I even put it?
Your washing machine's in the kitchen, right? Like most British houses.
No, a really small utility room adjacent to the kitchen. Not really got any extra space unless I knock down a wall. Yeah, so we're probably going to have to just park that filter for, at least for us two. But imagine a cocktail of bacteria that you chuck into your wastewater. One, to get rid of some of the organic waste and produce, your biogases to use for energy. And then maybe you get your plastic fibres out using a different bacteria. And then we just have clean water, right?
In the future, far from now, that's what we're aiming for.
I would say it's not that far in the future, because this enzyme-based technique does have a pilot plant. And they've got 100% fibre-to-fibre biorecycled clothing line. And they've done it with Patagonia, Puma, and some other brands. So they've done it. They've made a t-shirt out of an old t-shirt.
So it's like 100% efficient if you're saying fibre to fibre. There's no loss at all from that process.
No, I think what they mean is they didn't have to use any virgin material to make it.
Okay, but they started off like an extra large t-shirt and they came out with a small t-shirt.
I suppose maybe that, yeah. But it's gone. So this pilot plant has been going since 2021, and they're actually thinking of making one in the UK as well. So they're expanding, and they're making a actual industrial scale one in France.
And this is chemical recycling?
No, this is using an enzyme.
Okay, but it's still breaking the polymer down into monomers to then...
Yes.
remake your polymer.
Correct, yes. So the bacteria has two enzymes, sorry. One is the one that breaks down PET, so PET-A's, and then that produces MHET. And the second enzyme is an MHET-Ase, and it produces ethylene glycol and terephthalate acid.
Okay, so it's a two-step process. That sounds like it could take a fair amount of time.
You would be correct. It is a bit slow. In one of the papers I read, it took a few hours to convert like 9 grams.
Okay, whereas this new research using the microwaves takes 15 minutes, although it was only half a gram. I don't know if you'd scaled it up if it'd still be 15 minutes. Still.
Well, what amazing other researchers have done is they got the structure of that bacteria, which was Idenella saccharinensis 201F6.
Well, that's a very exciting name.
Yeah.
You hear the sarcasm in my voice. Call it Bob or Chris or something, or Danny.
Yeah, maybe there'd be too many Dannys because they basically modelled it and then altered it so it'd be faster. So then what do they call that? Danny but faster.
Danny fast. I don't know.
Danny go fast.
Yeah.
And then Danny gets super fast.
Danny Sonic, yeah. I'm sure you could do some sort of video game type progression of your bacterium.
Level 1, level 2. So yeah, it definitely was more promising that they could make it faster, essentially. Whereas I think for chemical processes, it's just make it hotter.
Yeah, and then I guess you run into things like, I think this process that I was reading about is at 210 degrees C. I think that's like the point at which the nylon starts to break down or melt, which isn't that great.
And then it got in the way, I guess?
I think so, yeah, and it's this kind of goo that had to be separated out somehow, which meant the nylon was degraded, which then means you need to do more processing. But it's all just chemicals, right? So you can develop a process to deal with most chemicals, I think.
Yeah.
I was also under the impression that techniques that use bacteria or enzymes, they don't work quite so well if you've got mixed fibres in there. I can imagine that the enzyme or the bacterium likes to sit on a surface, and if it's sitting on the surface of some cotton, say, it's not going to do its job to break down the PET unless that PET also happens to be sitting on the surface of the cotton. I don't know if that's just my brain making things up, though.
I'm trying to remember what I read about this, because I think their aim was also for mixed fibre recycling.
Oh, okay. So are they actually able to do mixed fibre recycling now, or is it an aspiration?
I'm just going to make funny faces until I remember.
Okay. If you don't know, that's fine. I mean, the reason that I ask is the research paper I was reading from June last year says that they're the first to do this sort of chemical decomposition without sorting the textiles first.
Yeah, I just cannot remember what I had read.
Maybe we can revisit this in a later episode then and look at more enzyme-based techniques and how they work and how advanced they are. I'm intrigued by this industrial scale plant. Was it industrial scale or pilot scale that you mentioned?
It was pilot scale, and they're building an industrial scale. The main focus of the research was identifying better bacteria containing these enzymes and which one was sort of the fastest and which had the best reaction mechanisms. So no, it wasn't really going into detail of what happens when you have mixed fibres.
Okay. Just the biological side. I was under the impression that they could, having extracted the enzyme, they could then essentially synthesize the enzyme and tweak it to make it more efficient.
Yeah, so I think they were comparing versions of them because I suppose enzymes are kind of named by what they react with. I don't think that limits like what structure it actually takes. This is where my biology fails me.
Do you mean that you could have enzymes of different structure, but they would still break down the same molecule?
Yes, that is what
Right.
I mean.
Okay.
So they picked out different bacteria that also had enzymes that did the PET breaking down process. Yeah, they found different bacteria that eat PET, essentially.
Okay. And they've evolved to do this because there's a lot of plastic in the world and there's a lot of plastic in the environment.
Yeah, one of the scientists that discovered it was analysing wastewater with plastic in it, and that's how they found the enzyme.
Ah, nice.
We put the biological process aside, this research paper that we started off with on the chemical recycling of mixed fibres, I quite liked that this paper covered a lot of different topics, that it almost was multiple papers built into one, that they didn't just look at the reaction of zinc oxide and PET, but they then looked further than how different fibres reacted. And then even further, they decided to see how would that actually look like if they built a chemical plant around it.
This is what I quite like. They're already thinking about that end point and how do we get to an industrial process. They're not just sitting in the lab going, well, I've got my half gram of textile and I've made like 95% pure PET out of this. Job done.
I suppose that's kind of what a chemical engineer does, is there's a reaction, but then, okay, what is actually the optimal reaction pathway to make it a viable chemical plant?
I can see that because there could be so many steps to your industrial process, to start off with random clothing that people have tossed away, to all your pure different components, so your cotton, your nylon, spandex, and your PET monomers.
And then if you even recycle the ethylene glycol that you put in to then make your PET again.
Exactly, and what do you do with all the dyes, and how do you deal with all the different pre-treatment methods that have been applied to the fabrics, like UV resistance, that sort of thing. So you need to think about all those different aspects if you want to see a real-world result.
I mean, it's like hard to imagine some of these things because until you're in it, you don't really understand. But they were looking at a throughput of 500 kilograms per hour, and the operating cost being $92 million.
In what, the same hour?
I don't think that's in an hour, but if that was an annual cost, that's a lot of investment requirement.
You said this research article, the paper, covered all these different aspects. It sounded like someone's entire PhD was my take on it, because they looked at all the different variables, and it definitely sounded like 4 years of work to me, at least. And then there was this techno-economic assessment that you just mentioned that I kind of thought, well, that seems really brief, and I'm not an expert in this, and I think I need some more detail to really understand what you've done there. Here are some really big numbers. It's all I got out of it. They had like two different scenarios. In one scenario, you've just kind of, I don't know, increased the resale value of your item by saying we're just going to charge as much per unit. And I don't know if that's how these things work, because surely the market has to be willing to pay that price. It's not really sciencey or engineering at this point, though. It's economics.
Interestingly, my chemical engineering degree did involve these kind of economic assessments of your process, because then you'd then decide, you know what, I'm going to change which process step I'm going to take. I'm going to actually not use that and find a different way, or, you know, what purity do you aim for because of what selling price you have. So, funnily enough, economics does fall into my degree a lot.
Okay.
And maybe this is the difference with it being an engineering degree.
So you understood this part of the research article better than I did then, I guess.
Yeah. This kind of felt like my bread and butter much more than the biological enzyme process that I was reading. There was a lot of squiggly spiral models.
Whereas me being a scientist with a PhD in computational chemistry, which is basically staring at squiggly spirals on a computer for 4 years, I was much more at home with the biological stuff.
Oh, we read the wrong papers. But anyway, yeah, it definitely seems like a full study. Questionable about the price. I don't know. Maybe that needs some more optimization.
They're at lab scale at the minute, so I don't know how well considered those costs are, if they'd be further refined the further along they get in the research. That's how these things work, right? Your costs get more accurate the further on you go through the work.
Definitely. And maybe there isn't even a market for recycled monomers yet. Maybe everyone just buys the pure stuff, and you have to kind of add that environmental green price tag.
Well, that's it. I mean, I feel like there has to be some stronger motivation for stopping people from extracting fossil fuels and pushing them towards using recycled material. We've extracted so many fossil fuels already. It seems daft to then just stick them in landfill.
I totally agree. I saw a fact in one of the articles we were reading as the prep, and a study estimates that 8.3 billion tons of plastic have been made in the history of since we've been making plastic.
See, I can't visualise that at all. the only metric I have for any of this, because I'm also a nuclear scientist, is that all the nuclear waste that we've made in the UK so far that government wants to bury underground would fill Wembley Stadium.
Okay.
And every single year, as household waste, we produce a much bigger volume of waste than Wembley Stadium. Much, much, much bigger. And plastic's just one part of that.
Where does it all go?
It's weird when you think about it, isn't it? Because as an individual, you probably don't produce that much waste, but billions of people in the country, that all adds up.
In the world, yeah.
Yeah. And you hear stories of like lots of clothing, like fast fashion, ending up just floating around the Atacama Desert because no one has anything else to do with it really, so it just gets dumped there.
Well, hopefully, with this pilot plant by Carbios and, all the research into enzymes, that we would be able to clean up some of our mixed waste, or at least recover a PET.
I think it sounds like an emerging technology, and I guess it's, are we going to use enzymes to do all this work, or are we going to use microwaves and catalysts to do it? Or can they work on separate waste streams? It's definitely one to watch, I think.
Yeah, there could be different applications for them. Say one of them might have a better affinity for certain wastes. Yeah, so I think let's draw this conversation to a close. We've discussed a great piece of research that looked into a chemical recycling method for PET fibres, and it has the potential to work with other fabrics mixed together, or fibres mixed together. So it has great potential, but it's still in the early stages of research.
Yes, I'm going to pay more attention to this research, I think, and see what happens next.
I agree. I think we should definitely keep an eye on this topic. Thanks for listening, and see you next time.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.